think I started recording. Yeah. Okay. Hello and welcome. Let me stop share. Okay, we are in the home stretch. We're almost there. Two more meetings. When I set up the meetings on Canvas, it will, tell me how many, scheduled meetings there are. And this is meeting number 10 of 13. Can that be right? 10 of, we have two more after today. That's weird. I think it said 13. Anyways, we will talk about some good stuff today. Let me try to move it to the other screen. Oh, I gotta shut off the music. I'm sorry, I can kind of hear it in the background still. Ugh. Oh, I'll find it, trust me. Maybe I won't find it. Where did it go? Oh, sorry. Just a moment. What a mess my computer screen is. Well, I guess my room just came to temperature. It's not that hot out at all, but I turned on my air conditioner to try to have some white noise in the background because they are digging up the street in front of my house right now. So there's a little more ambient background noise than normal. That's what's going on. Sorry about that. So let me. So on our course page, here we are, Wednesday, June 23rd, 9 a.m., chapters 8, 9, and 10. That sounds crazy, but it's not really that crazy. There's only like a couple of questions in some of the chapters, so nothing to be too concerned about. And then after we go through that, I will be fielding any questions people have from chapter 6, because we're going to have a quiz on chapter 6. And you can start populating the chat with those questions if you like. We will go over things there. What's coming up, what you should be aware of is that 1 week from today is our last meeting time, and that will be exam number 2 on chapters 6 through 10. So we have chapter 6 and we're going to have the quiz on chapter 6. We did chapter 7. We don't have a separate quiz on that. And then chapters 8, 9, and 10 we're going to talk about today, with the idea that you then have this block of time between after the quiz today and class on Monday to go ahead and tackle those homework problems and see if there's anything you're confused about. Once you do the homework, you may want to then just go ahead and start plugging away with the practice exam. The practice exam right now might look, some of this stuff probably looks like insanity to you right now. What are these Greek letters and what are they talking about? What's this stuff spinning around? We will talk about that today, try to set it into a context for you to be able to deal with it. But as you go through the practice exam, there'll be some questions that you're able to do right now, some questions that have appeared on the homework and maybe are appearing on today's quiz. So make sure you, you know, got those down. And then there's some other questions, like we talked about work and energy last time. So if somebody has a mass of 75 kilograms and climbs the stairs, gaining 2.5 meters in height, how much work was done? Well, work equals the change in gravitational potential energy. Gravitational potential energy is mgh. So we're given an m. We know that g is 9.8 meters per second squared, and the height is 2.5 meters. So that's a fairly straightforward question and pretty easy to put on an exam. This question is just from the chapter 7 homework. So you should be able to tackle that. But then as you go down further in the practice exam, you'll see questions on torque. Well, we haven't talked about torque yet. What's that? This crazy thing, what's I? I don't know what that thing is and what's going on here. Well, we'll talk about that. So there's some questions that we haven't tackled yet and some questions that you should be well prepared for. So, work through the practice exam, and then on Monday, we can do the, homework questions you have questions on, the practice exam questions you have questions on. Hopefully clear up any confusion you have and get you in a position that you're ready to hunker down, carve out whatever time you can between Monday and Wednesday to prepare yourself for exam number 2 on chapters 6 through 10 material next Wednesday. And so every week of the class is listed here, and you can click on next week and see that Monday we'll meet and we'll talk about those questions you have. Wednesday we'll meet and you'll take exam number 2. Also, time's flying by, so do take a look at either the assignment tab or the syllabus tab, and just make sure that you have done everything. The due dates that are set so that they will show up for you to see, oh, this thing is due coming up, I should do that. But once we get significantly past it, maybe it doesn't show up for you anymore. So just, go through and make sure you've done everything. That if it's late, it shows up in a different color, but you still get the points for it. So do that, make sure some of these things we're still kind of talking about. So maybe you're not able to do the labs quite yet, but pretty close. So keep plugging away. We're almost there. It's going to be over soon. And that's a good thing. Okay. Let me view reading view and new share the PowerPoint. Okay. What to say about this? Isaac Newton, in putting together into a coherent package our understanding of kinematics and dynamics, what we call Newtonian mechanics. There were some key foundational pieces that had to be set into place. Among those are Newton's laws of motion. Among those are understanding of force and energy and whatever. And then there are some things, what we're going to be talking about now with momentum, it's not new, There's no new units. There's no new foundational concepts. It's just taking some of the foundational concepts that we've already talked about and developed and applying them to different unique situations, such that for the, so far we've had a thing is moving or a force acts on a thing. And thus far, we haven't had two things kind of smash into each other. So it's two things smashing into each other, but other than that, it's no, major new concept. So let's explore this a little bit. And that's why we can handle a few different topics on one day, because we're kind of filling out what we have for a foundation. We're not, hey, here's a totally new concept that you've never thought of before. So if we were in the process of taking calculus-based physics, I might take this time to discuss with you the area under the curve when the curve is some crazy shape like this that we'd have to describe with some polynomial. And that would be fun and entertaining, but kind of pointless in a way, because truly for the bat striking the ball and then the ball going flying, of course, the ball will hit the bat and like barely be touching. And then as the bat moves and the ball starts moving with the bat, there's a huge amount of force. And then just before the ball goes flying off of the end of the bat, it's a tiny amount of force again. But truly all that matters is the average force for that period of time. Hold that thought for a second. So here is the definition of impulse. So I think I have revealed to you already that physics is a little bit obnoxious sometimes. And so this is one of the ways that physics is obnoxious. Surely you have noticed that when we have a lowercase m, that used to stand only for meters. So, you walk 25 meters or whatever, meters per second squared. Lowercase m was our unit for meters. But then when we started talking about forces, lowercase m was also the symbol in the equation F equals ma. And in that case, it stood for mass. So what is it, mass or meters? Make up your mind. Well, in the equation, the variable m stands for mass in kilograms. In the units for an answer, m isn't a variable, it's the unit for meters. So you just gotta make a distinction between variables and units. So the unit J is joules for energy, but this is the variable J in an equation. J is impulse. Why not I for impulse? Well, we use I for something else coming up a little bit later. Just kind of the order that these things were kind of laid out there. So J is impulse, and what impulse is a force, average force for a period of time, and that's going to act on an object. So impulse is a vector quantity, and it has the same direction as the average force. So if you give something a shove, you have given it impulse. If you're a Star Trek fan, then maybe, impulse engines and stuff. This term is not brand new to you, perhaps, but it means kind of what you think it means. You give something a shove. That's impulse. Oh, I guess maybe impulse if you're impulsive. Maybe the same kind of root, but totally different context. All right, so impulse equals force times the average force times the time that that average force is being applied to the object. Okay, set that thought aside for a second. They will come back together. There's a thing called momentum. Momentum, I think, means what you think it means, right? You know, when I graduated from college, I packed everything I owned into my Volkswagen Bug, and everything I owned at that point fit inside a Volkswagen Bug. And I drove down to the end of the street where there was a stop sign, and I stepped on the brake, and my car was not slowing down quite as quickly as I was used to. Why? Well, because there was a lot more mass in the car. And in order to change the velocity, it took more force. So my car had more momentum. It was the same size car, but I had my stereo in there. Back in the day when a stereo was an amplifier and speakers, and like, there's a lot of mass in my car, and it had more momentum. I always think of momentum, if you've ever gone on a hiking expedition in the woods or climbing a mountain, you know, it's all well and good if you're just kind of hiking on a trail, but then when you strap on like an 80-pound backpack with, you know, tent and food and survival supplies, you notice if you're walking down a hill that suddenly you have a lot more momentum. There's a lot more mass on you, and for the same velocity, you know, there's a bigger bigger thing. I don't know what other word to describe that. But you know, if you've ever driven a really heavy moving truck, you can feel that you have significant momentum. Anyways, linear momentum of an object is the product of the object's mass times the object's velocity. And that's a thing. And there's no new units here. So I guess I've already described how we're using the letter M all over the place for mass and meters. So M was not available for momentum. So why not break out a lowercase p? So lowercase p for momentum, the product of mass times velocity. It's a vector. Mass isn't a vector. Mass is a scalar quantity, but velocity has magnitude and direction. So momentum has direction associated with it. It is a vector quantity. But no new units, just product mass, kilograms times velocity, meters per second. Kilograms times meters per second is the unit that we will use to describe momentum. Now, bringing these two things that we've talked about so far, hopefully this isn't a big mystery to you. We're talking about the impulse momentum theorem. We defined impulse, we just defined momentum. Now we're going to bring them together. So Newton's second law, that's a fine place to begin. Force equals ma. Acceleration is the change in velocity over the change in time. So if we plug that in place of acceleration, we get force equals mass times final velocity minus mass times initial velocity divided by time. And then if we multiply both sides of the equation by time, we get force times time equals mv final minus mv initial, which is what we've been talking about, that impulse, force times time, equals the change in momentum. That is the impulse momentum theorem. So if I have a ball and I want to throw it, well, the ball is going to have a change in momentum. It has mass and it's going to undergo a change in velocity. and I can figure out, at least estimate, the force that I'm throwing it at. If I have some timer or something, some way of figuring out for how long my hand is in contact with the ball, and I can figure out the change in velocity of the ball, then I could figure out the force that I applied on the ball to throw it. So force times time equals change in momentum. So I don't know that I love this example. Here's the thing with momentum is there are cases where momentum is conserved if all of the forces involved are taking place between the objects involved. If there's two objects colliding with each other, then the initial momentum will equal the final momentum. And I think for purposes of illustrating that fact, we will deal with primarily with situations where we say they're all internal forces. Now, conservation of momentum, if I have a ball and I drop it and bang my computer, hopefully I did nothing bad. If I have a ball and I drop it, well, its initial momentum was 0. Its final momentum was something when it hit the table. So momentum increased. There was none and then there was some. So momentum is not conserved because there's an external force. All I'm looking at is the ball. So the ball and then the gravitational force of the Earth are interacting with each other. And so the gravitational force of the Earth in that case is an external force, as opposed to, in this case, two balls colliding with each other. If two balls collide with each other, we can figure out conservation of momentum in terms of the two balls interacting with each other. But in this example, they're also falling down out of the sky. It's awfully complex. So there's no conservation of momentum in the y-axis. There is conservation of momentum in the x-axis because x-axis forces are existing between the two balls. Don't get confused. Hang tough for a minute. We will make sense of this. So if the external forces involved were 0, and typically in lab, what we do is we have this flat track and carts that roll back and forth on the track. And the carts smash into each other and maybe they bounce off or maybe they stick together. And we analyze the situation in terms of conservation of momentum, because for the most part, we have eliminated external forces. The carts aren't falling down out of the sky, friction is minimized. So we have a case where we can talk about momentum for an isolated system, just two objects interacting with each other and doing our best to eliminate friction and other things. So here we have two ice skaters. They are starting from rest. And since they're on the ice with nice sharp skates, we're going to say that friction is negligible. We can pretty much ignore friction. One of these people is a 54 kilogram person. The other one is an 88 kilogram person. And the 54 kilogram person moves away with a speed of positive 2.5 meters per second. 2.5 meters per second. And that's positive because it's in the positive x-axis. This person, who has a mass of 88 kilograms, is moving off in the negative x-axis, and we want to find this person's velocity. And we're going to do that by way of conservation of momentum. Momentum before equals momentum after. Before and after what? Well, before and after they push off of each other. Initially, it's two people standing still. Momentum is the product of mass times velocity. So if they're standing still, the velocity is 0. So the initial momentum is 0 equals what? Mass 1, velocity 1 plus mass 2, velocity 2. 0 equals 88 times V1 plus 54 times 2.5. 54 times 2.5 is 135. All right. We want to get V1 all by itself. I'll subtract 88 V1 from both sides of the equation. I'll get negative 88 V1 equals 135. And then I'll divide both sides of the equation by negative 88. 135 divided by negative 88. And I get negative 1.53 meters per second. This, the big person has a velocity of 1.53 meters per second in the negative x-axis. The combined momentum of the two people is positive 135 and negative 135. Negative 135 plus positive 135 is 0. Momentum is conserved. It's 0 momentum at the beginning and 0 total combined momentum after the push. But this person is carrying off an equal amount of momentum as this person. But since momentum is the product of mass times velocity, and this person has less mass, they must have more velocity, and this person has more mass, has a lower velocity. And they have to be in opposite directions in order to have it add up to 0. All right. So when we're dealing with conservation of momentum, we're going to decide which objects are the system, and it's a problem if you have the Earth, gravity, and an object in the same system, because that's really complex to deal with. Relative to the system, you want to identify the internal and external forces. So if you can have all isolated internal forces, then you can do this trick where you're going to set the final momentum equal to the initial momentum and treat it as a vector quantity. There are different types of collisions. There are elastic collisions. A perfectly elastic collision would be like an ideal scenario. And in a perfectly elastic collision, we'll find that momentum is conserved. Momentum is always conserved, but also kinetic energy is conserved, 1/2 mv squared. In an inelastic collision, we'll find that momentum is conserved because it's always conserved, but in an inelastic collision, kinetic energy disappears. The kinetic energy that went into the system can be transformed into a different form of energy, usually like heat and sound. Yeah. So Railroad cars, when they collide with each other, they collide and stick together. We have a case where initially car B here is at rest. And so it has 0 momentum, but car A has momentum. It's traveling at 24 meters per second. Now, if both cars have a mass of 10,000 kilograms, what do you think the final velocity is? If car A comes in, mass of 10,000 kilograms at a velocity of 24 meters per second, strikes another car that has a mass of 10,000 kilograms, and they collide and stick together and keep moving, what's that final velocity? I think I told the story about my wife taking the MCAT, the medical college admissions test, and going into that exam thinking that all physics answers are counterintuitive, and she wound up doing the best on the physics section of that exam. And I would like to have you believe in your heart and soul that physics can be intuitive, that it does make sense. So I think the intuitive answer here is, probably 12, right? We're going to cut the velocity in half. Two things equal mass will hit each other and will go off. And so the initial momentum equals the final momentum. The initial momentum is mv, 10,000 kilograms times 24 meters per second. So 240,000, 24 times 10,000, 240,000 kilograms times meters per second, 240,000, sorry. Afterwards, we have 10,000 plus 10,000, 20,000 kilograms times V final. Momentum's conserved, that's 240,000. So V final equals 240,000 divided by 20,000 kilograms times meters per second. And that is 12 meters per second. It is the intuitive answer. The final velocity was cut in half. Collisions in 2 dimensions mean that momentum is conserved in both the x-axis and the y-axis. For billiard balls, both things keep moving independently, and it becomes a very complex calculation. What we have on our practice exam is 2 cars colliding with each other and sticking together. And that is less complex. If they collide and stick together, then it's just less math. And so we're illustrating the concept on the practice exam without pages and pages of math, which I think makes life a little bit easier. Okay, and we'll take a quick peek at that before we part ways on this topic, or on today's lecture material. One item that just doesn't have an easy place to fit in the course material is center of mass, but it kind of fits in the context of this 3-chapter lecture. I have a ruler here, and this ruler has a place on it where I put my finger and it balances. I have the ceiling fan on as well, so we got a little action from the airflow in the room. But I put my finger at the center and it balances. Now, if I didn't put my finger at the center, so if I do put my finger at the center, a linear force will give linear motion. And that's the point of this concept of center of mass. There is a place on any object, even irregularly shaped objects, of which I don't appear to have any handy. But an irregularly shaped object, you can find a certain point on it where you could balance it. That's the idea of center of mass. I guess I can take the ruler, it's a little bit floppy, but not too bad. And I can put a penny on one end and I would find that it balances now somewhere not quite at the center, but closer to where the penny is. Why? Because the mass of the penny is so much greater than the mass, the density of the material that the ruler's made out of, that I've shifted the center of mass over toward the penny side. Now, the center of mass idea is that if I apply a linear force at the center of mass, I get linear motion. If I apply a linear force somewhere other than the center of mass, I get rotational motion. And that's kind of the transition into our next material. But center of mass, also known as center of gravity, is the point at which an object will be balanced. And then we'll talk about torque in just a second. So, blah, blah, blah. Okay, now, while we're still going, we're not even up to the hour mark yet. We're doing good. Statics and torque, and this is fairly straightforward. According to Newton's second law, a force causes an object to have acceleration, but what if your objective is to have angular acceleration? Imagine, if you will, that you arrive at a door and you want to open it. So you want it to rotate on its hinges. You're not trying to bust through the door like the Hulk or something. You're going to turn the doorknob, which is its own exercise in torque, but then you're going to rotate the door on its hinges. So what's going on there? Well, you're applying a linear force in hopes of generating angular acceleration. You want the door to rotate open. And there's different ways you could apply the force. I'm sure I'm not the only person in the world who's arrived at a glass door and you go to push the door open and it turns out you're not way out at the handle side, you're in closer to the hinges, but you keep pushing anyways. You have to push wicked hard. If you've not done that, you should try sometime. If you push close to the hinge, you have to push really hard to get the door to rotate open. Whereas if you push way out where the handle's located, and handles tend to be located far from the hinges, far from the axis of rotation, you'll find that it doesn't take nearly as much force. And then it's just silly if you're trying to open a door and you're like leaning, into the door, into the hinge or something. That doesn't cause rotation. So torque, this Greek letter tau, is the product of force times, this is the cursive L standing for lever arm. It's also the distance, if the distance from the axis of rotation is the radius. So sometimes you see FR, force times radius, the distance from the axis of rotation. Other times you'll see an L for lever arm. And that is what causes rotational motion, rotational angular acceleration, making the door open. So there there's acceleration, linear acceleration that we can have in the x-axis or the y-axis, but then there's angular acceleration, alpha. And so if it's not rotating, if it's not moving, then we say the acceleration is 0. And if it is, then we have some acceleration. I don't know that we need the diving board example. We have a much better, this is a terrible example of torque, just because we don't have a good angle. So I'll talk about torque, net torque perhaps being 0 or having some value on a practice exam question. And the good thing about the practice exam questions is that there's also the solutions available to you and a video of me talking through the solutions. So this is closer to the example that we have from our practice exam, where what we're going to talk about is there's torque downward rotation, which is clockwise rotation. Clockwise is negative, counterclockwise is positive. There's negative clockwise rotation due to the torque from the physics book, which has a mass of 4 kilograms. So 4 times 9.8 is the weight of the book, located 38 centimeters from the axis of rotation. Then the arm itself has mass 2.5 kilograms. Its center of mass, that concept from the end of chapter 8, center of mass is located 16 centimeters from the axis of rotation. So those two together are sources of downward torque. And then the upward torque is from the biceps muscle. That's only 4 centimeters. It's attached pretty close to the axis of rotation. And so we could figure out the force required from the biceps muscle to hold this steady, or if we had a value, we could figure out what the net torque would be and how things would rotate if we let that happen. And I will do the run through of the practice exam and the homework questions in just a moment. The last concept, the last ideas that we have is mostly this idea of angular mass. We have mass, right? Mass in kilograms, but it matters how that mass is distributed around an axis of rotation. And so there's a concept called moment of inertia, which is also kind of known as angular mass. So first of all, I think we've touched on this idea already, that there are 4 equations of kinematics for linear motion. There are likewise 4 equations of kinematics for angular motion, just changing the definition. So instead of linear velocity in meters per second, we have angular velocity in radians per second. Instead of linear acceleration, we have angular acceleration. Instead of linear distance, x in meters, we have angular distance, theta, in radians. Radian is just a different way of measuring an angle. It's referencing a specific fraction around of a circle for things that move in circular motion. And that's it. Velocity, acceleration, angular distance, and then time. Time is always just time. So we have 4 equations of kinematics for linear motion, 4 equations of kinematics for angular motion. We also have some relationships. between linear motion and angular motion that will be relevant on today's quiz and are relevant in general. The relationship between linear velocity and angular velocity, linear velocity equals the radius times the angular velocity. So the radius will be some value in meters, maybe half a meter, maybe 3 meters, but something, times radians per second. So meters times radians per second, as we're translating from linear and rotational velocity, the radians just disappear and we get a velocity value in meters per second. So when we're figuring out linear velocity based on angular velocity or angular velocity, and we're given the radius, we can freely go from one to the other. So the angular velocity is linear velocity divided by the radius, and that will turn into units of radians per second. And likewise, linear velocity, meters per second, is the radius times the angular velocity. It's a very good idea to get the quiz done before Monday, but at the conclusion of the lectures today, which we're not too far off from, I will remain here on Zoom chat to clarify questions and help you get through the quiz if you're having any issues. Okay, so it turns out that in terms of rotational motion, when we want to think about the thing that's spinning around, it matters how that mass of the thing is distributed around the axis of rotation. And so the simplest definition of angular mass would occur when all of the mass is located far from the axis of rotation, all in one kind of well-defined spot. And we would call that moment of inertia, capital I, angular mass, would be mr squared. That is one definition, and that's the simplest one. There are all sorts of moments of inertia. You can have mass distributed around an axis of rotation in all sorts of crazy ways. And ultimately what we're doing is adding up the contribution to the net torque from each molecule, mass of each molecule of the weirdly shaped object that is somehow spinning around. Now we don't really have bizarrely shaped objects typically spinning around. So getting there, we're gonna be there. In this really difficult to read chart, we have some moments of inertia for objects that you can kind of define pretty well. So a hoop is the thing where all the mass is way out at the edge, far away from the axis of rotation. And that is the I equals mr squared. There's also this thing that's a lot more like a hockey puck, say, where the mass is evenly distributed throughout. And that, kind of, as you might expect, 1/2 mr squared. So a hoop and a hockey puck, those are things you can imagine. And then when you have a ball, so sphere, let me go to this one because it's easier to see. If you have a solid sphere, so this is like a bowling ball, that would be 2/5 mr squared, versus this one, which would be more like a basketball, thin spherical shell. So a sphere, but the material is all out at the edge. That one is 2/3 mr squared. Fairly complex math to add up the contribution to the torque from each molecule. But once that's done, we just have these values that we can use when we're doing our equations. All right. Then it's the whole course all over again. Turns out that there's a rotational version of work. Work, you remember, was force times distance. Well, angular work, instead of force, it's torque. Instead of distance, it's theta, angular distance, in radians. And that's angular work in joules. So rotational work in joules. Same concept, just, with different perspective. Same deal with kinetic energy. Instead of 1/2 mv squared, it's 1/2 I omega squared. And I, remember, is moment of inertia, and moment of inertia can be defined differently for different objects. So definition of rotational kinetic energy. Kinetic energy for something that is rotating around, 1/2 I omega squared. Same unit, joules, just if you throw a rock versus something that's, rolling or spinning, has different terminology that we would use. For things that are rolling, not just spinning, there's both linear momentum, linear kinetic energy, and angular kinetic energy, and both have to be accounted for. And it makes a difference how the mass is distributed around the axis of rotation. The solid cylinder has an angular mass of 1/2 mr squared. The hollow cylinder, remember, was just mr squared. So the hollow cylinder has more, for the same total literal mass, they both have a mass of 1 kilogram, but for the same literal mass, the hollow cylinder has more angular mass. It takes more energy to get it to roll, to spin. And so if you set these up, and this is a demo I will frequently do, if you set these up at the top of the hill and then let them go, you'll find that the solid cylinder gets down to the bottom significantly sooner because of the difference in how the mass is distributed around the axis of rotation. Walkthrough of the math you would do to figure that out. That's that. Angular momentum. So we talked about momentum equals mass times velocity. Angular momentum equals angular mass times angular velocity. Angular momentum is also conserved. That means if you change the way the mass is distributed around the axis of rotation, the angular velocity will change. So we sometimes see that with figure skaters. Figure skater starts a spin with arms and leg kind of out from the axis of rotation, spinning probably faster than I could handle, but not nearly as fast as they can. And then when they pull their arms and leg in tight, now the moment of inertia is significantly smaller because it's mr squared. So when you change the radius squared, you're doing a huge difference. So when you change the radius, then you will have a faster, and you see that often, they spin faster when they pull their mass in. Whoo, maybe that was bad, but that wasn't my intent. but I said it wasn't as bad as it sounds, and maybe it was just as bad as it sounded. Let me quickly, while you're still kind of hanging on by a thread, Chapter 7 homework. Chapter 7 was last time. That's not what I want to look at. Chapter 8 homework. I experimented with stop motion photography for making these homework videos, so they are kind of goofy. Have mercy on me. So the train has a mass of 15,000 kilograms and is moving at 5.4 meters per second. So there's momentum, right? Mass times velocity. We want to find the time required for a force of 1,500 newtons to bring it to rest. So impulse equals change in momentum. F delta T equals mv. So force time equals change in momentum divided by the force. I show one skater is moving at 4 meters per second. The other skater is stationary. They collide by one person jumping into the arms of the second person. They collide and stick together. So we can figure out the final velocity of the two of them stuck together with just conservation of momentum. And then we can take the mass 60 kilograms mv squared, 1/2 mv squared, the 4 meters per second squared, for the initial kinetic energy, and then 60 plus 75, so 135, 1/2 mv squared. We know the final velocity for the two stuck together. We can figure out the final kinetic energy and then deduce how much kinetic energy was lost. Chapter 8, chapter 9. There's only 2 questions. Torque equals force times lever arm, force, lever arm, just that easy. This is a net torque. So the torque to the left of the seesaw and the torque to the right of the seesaw. And there's kind of a clever math trick in there. The two children are separated by a distance of 3 meters. So our challenge is to say that one of the children is X meters from the pivot point. The other one is 3 minus X. And to figure out then what X is, what the distance from the pivot point for the smaller child. And I walk through that one in the solution. And then finally, chapter 10. So doing some equations of kinematics with rotational motion and doing some stuff with moment of inertia. Just a couple of questions and there's video solutions. So the other piece that I wanted to mention before we move into quiz time, quiz questions, is that I have the solutions to the practice exam posted. I don't recommend looking at those right away. It's better for you to work through the questions first and then, check the answers and see what you understood and what you didn't understand. Ugh. All right, maybe we'll just go to the questions. I don't know why the answers are harder to look at, but conservation of momentum with the football players here as opposed to ice skaters, so it's similar. You want to figure out which one has a greater rotational energy at the bottom. The arm question is the one kind of talked about in terms of concepts, but you can see a worked out solution for that in the answers. And here we have two cars that are colliding and sticking together. So all of the x-axis momentum is carried by this red car, so mv momentum. All of the y-axis momentum is carried by the blue car, mv momentum. They collide and stick together. So the total momentum is a squared plus b squared equals c squared. It's the c value for the total momentum. And we can figure out the direction based on that. And then in order to find their final velocity, we take total momentum divided by total mass. So the 1250 kilogram car plus the 1500 kilogram car, total mass. And that is done out in the solutions. Okay, now, we can step back. Chapter 6 homework is the general setting for today's quiz. I have a couple of questions that have come in already. If you have other questions, feel free to pop them in chat. One of the questions that I have already is number 2, and another one is 7 and 10. So number 2, microwave ovens rotate at a rate about 6 revolutions per minute. What is this in revolutions per second? Well, 6 rev per minute. What do I want to do? I want to get rid of minutes and turn it into seconds. So I want seconds to be in the denominator and minutes to be in the numerator. And there are 60 seconds in 1 minute. So 6 divided by 60, 0.10 revolutions per second. What is this velocity in radians per second? All right, well, I'm part of the way there. 0.10 revolutions per second. Now I want to get rid of revolutions and turn it into radians. There are 2 pi radians per revolution. So 1 revolution is 2 pi radians. 2 times pi is just 6.28. So 2 times pi times 0.1, 0.628 radians per second. Truck, 0.42 meter radius tires traveling at 32 meters per second. What is this in radians per second? So V equals R omega. We want to get omega. Omega equals V over R. V was 32 meters per second. Radius was 0.42 meters. 32 divided by 0.42, 76. radians per second. And then we just have to like do the opposite of what we did up there, right? So we want to get this into revolutions per minute. I want to convert radians to revolutions. So I want to cancel out, there's 2 pi radians in 1 revolution. So that's 76 divided by 6.28, 12. What is that? Radians per second. And then I want to get rid of seconds and turn it into minutes. So 60 seconds in 1 minute. So 12 times 60, 729 revolutions per minute. Number 10, have a radius, want to get to RPM that is 1.5 that due to gravity. So we want an acceleration, centripetal acceleration that is 1.5 times 9.8. 1.5 times 9.8 is 14.7. So centripetal acceleration equals v squared over r. So v equals the square root RAC, square root of the radius 8 meters times centripetal acceleration of 14.7 meters per second squared. We're going to get 8 times 14.7, the square root of that is 10.8 meters per second for the velocity, the linear velocity of the thing spinning around. And then we can get angular velocity, omega equals v over r. So 10.8 divided by 8. Angular velocity is 1.35 radians per second. And then same process that we did, we can convert that into revolutions per minute. It's this relationship between rotational motion and linear motion that we're kind of messing around with, and the idea of centripetal force. All right, those are the questions that I have from chapter 6 quiz, homework material before the quiz. Are there any other questions before the quiz? All right. I will stay here on Zoom chat. I'll stop recording.